Professor Jevgenijs Ivanovs did his PhD at University of Amsterdam and URandom, and he is currently a professor at Aarhus University. Something worth mentioning here is good news last year that Jevgenijs was awarded the highly prestigious 2020 Olam Prize. The Olam Prize is a biennial award of the Informs Applied Probability Society, recognizing outstanding contributions to applied probability by early career researchers. He is the third researcher affiliated with URandom to receive this extremely selective award. And his title of the talk is Recovering Brownian and Jump Paths from High-Frequency Observations of a Lévy Process. All right, it's all yours, Jevgenijs.
Thank you for your nice words. Right, I'll be talking today about Lévy processes and high-frequency statistics, but in a bit non-standard way. So both the objective and the methods, they are rather non-standard, and I'll come to that later. So this is a joint work with Jorge González Cázares, and he's finishing his PhD with Alex Mijatovic at Warwick and the Alan Turing Institute in London. Right. What's the problem formulation? So we have a Lévy process X, so just a process with stationary and independent increments on a unit time interval. Well, you can take any compact time interval. And well, maybe let me mention right away that I will not assume any deep knowledge of Lévy processes. I was aiming when preparing this talk for a broad audience. So of course, when you know more, it's maybe you can see things at a deeper level. At the same time, I should excuse myself in front of experts. I'll be talking about some basic things, maybe for a prolonged time. So the basic Lévy-Ito decomposition says that we can always decompose this Lévy process X into two independent pieces. One is a scaled Brownian motion here, right? So sigma is just a non-negative number. Often I'll assume it's actually positive and just make some remarks when it's 0. So when there is no Brownian part. So normally we have it, right? And the process Y, once again, it's independent Lévy process and it has no Brownian part. People usually like to separate it further into small jump martingale and compound Poisson of larger jumps with drift maybe, right? But that's all that jump part and drift sits in this process Y here. Right, so as is usual in practice, we don't have full knowledge of the trajectories of the process X. Not to speak about W and Y, right? But normally, well, we assume that we observe the process X over a regular grid. We have n points, essentially n increments here, right? We have observations at x0, which is 0, then x1 over n, 2 over n, and so on, right? So you can also say we have the n increments of the process X. And high frequency means that I will let n go to infinity. And so we have more and more frequent observations, and then we can, of course, try to study our statistics, let's say our quantities, and try to determine convergence rates as n goes to infinity. So observations become denser and denser. And I should say there is a rich asymptotic theory. I just cite here a few papers. You see some prominent researchers over here, and there is also a book from 2012 by Jean-Jacques Philip Rotter about discretization of processes. So they, of course, they work with semi-martingales, but they look at very different questions. So I haven't yet explained what I want to study. Anyways, one of the basic examples is the quadratic variation of process X, right? And you normally take, say, some realized variation and study how it converges to the true one. Closely related is this parameter sigma. So you can try to estimate the sigma, and it can be consistently estimated with square root n, a square root rate, if y has paths of bounded variation. So here I should mention that y can be, there is a wide choice, so it can be anyways, so it can be something very close to compound Poisson process, or it can be something very close to actually Brownian motion on a small time scale. And when it becomes closer and closer to the Brownian motion, of course, estimating sigma will be harder. Right. But the question I want to consider here is kind of non-standard. I want to know if it's actually possible to separate the Brownian part and the jump part. So can we split, can we actually recover these basic components from the Lévy-Ito decomposition, in the Lévy-Ito decomposition, when we have the observations of X on a regular grid, on a dense grid? So one immediate problem is comes from Girsanov's theorem. In fact, even if you have full knowledge of the trajectories, it's not possible to separate linear drift from the Brownian motion, Brownian path, right? Well, Brownian motion with a linear drift can be seen as a Brownian motion under equivalent measure, right? So you cannot say almost surely what the drift is. But it turns out that apart from this issue, one can actually separate. And in fact, I'll discuss two methods. Mostly I'll focus on the first one, which was our starting point. It somehow is based on a surprising observation. And on the very last slide, I'll also mention the second method. So in fact, we first tried to couple a Lévy process with a Brownian motion. So we didn't start with this problem at all. And then we observed something really interesting, which I'll show you on the next slide. And then we tried to understand why it works, how it can be extended, and how it can be applied. And that's the way we arrived to this problem of trying to recover the components of the Lévy-Ito decomposition. But later, when the first draft was written of the paper, right, we looked once again at this problem, and then we realized there is also a much more direct way to do that. But well, it's direct, but still one needs to be careful and you know, introduce right compensators, let's say. And just because we had all this theory before, it was relatively easy to also treat the second case. But I'll talk about advantages and disadvantages of that second method in the very last slide. So let's go to this surprising part. I'll try to illustrate this then numerically. So here I have sampled two independent Brownian skeletons. So, well, just Brownian skeletons independently, right? And then what do I mean by skeleton is just a random walk with 1000 increments, right? So you have increments over this time 1 over n. These increments are denoted by this delta I, so that's the ith increment. And well, you can connect them with line segments or keep them constant in between. It doesn't matter. Or you can even append them with Brownian bridges, but it all doesn't matter. So what I do next is I reorder the increments of this gray thin W prime according to the increments of the red one. So what do I mean? I find a permutation, which will be almost surely unique, such that the ordering of these gray increments coincides with the ordering of the red increments. I mean, in this, for these two sequences, say the largest increment will have the same position, the second largest the same position, and so on and so forth, right? And the smallest will have the same position. So that's what I mean, the same ordering of increments. Then I just sum them up back to get another skeleton, Brownian skeleton, and look how it looks like. Right, so this is the surprising part. The trajectory looks very much like the red trajectory, even though it was sampled completely independently. Of course, it goes down. You know, the final endpoint coincides with this gray thin because the sums, they're just the same, right? I just changed the ordering of those increments. I can even bring the endpoints to the 0. So I will look at Brownian bridges so we can compare those two trajectories better. And you see they indeed almost perfectly coincide. So you can try n being larger and then you will not see a difference between the two trajectories. So this is the surprising part. Why is it so surprising? Well, I'm saying now that Brownian bridge almost surely is identified by the ordering of its infinitesimal increments. So it was actually hard to believe for us that this actually can happen, but it does happen. And when we were working on this project and trying to couple, so of course we first didn't try to couple Brownian motions, right? Brownian paths. We tried something else and things were not working so well. And at some point I made few calculations and I said, when going home, okay, Jorge, you just, we should drop it. It doesn't work. And luckily he was not lazy and it just takes 3 lines of code to reorder and the increments, right? And accumulate them back. And the next morning he said, well, but actually it works and works even too well. So then we try to understand and try to extend this observation to, and well, apply it to something. Right. So let me go back to this original problem. Now I have a Lévy process, which is, suppose sigma is known, right? Suppose sigma is just 1. I have a standard Brownian motion plus some noise or plus some jump part. Here in the simulations below, I took this Y process to be 1.2 stable. So it has paths of unbounded variation. It's not yet too similar on small scale to Brownian motion, so we should be able to somehow separate the two, but it's already a pretty complicated task. So once again, so the Brownian motion is in red, this jump part is in green, and I hope you can see the yellow is our process X. And this is only the yellow thing which we can observe and only at the grid points, right? Only deltas of X are known and nothing else. And the objective is to recover W and thus also the green stuff, Y. So what we do now, we reorder. So I simulate another Brownian path independently. I reorder now according to this ordering of the yellow increments. And this is how it looks like when the endpoints, when the endpoints are brought to 0. So now I compare the Brownian bridge, which is inside this yellow process, and the blue Brownian bridge, which we got by sampling independently another Brownian motion and reordering the increments according to the yellow increments. Right. So you see again they kind of match. But say the distance is a bit larger. Well, of course, it should be larger. You have some noise. Feel free to interrupt me. I'm fine with that. So let me summarize quickly what I do. So we have this Lévy process once again. Suppose sigma is known. If sigma is not known, you can actually estimate. That it can be done with as we'll see, with a faster rate. So pre-estimation of sigma will not spoil the rates I will present a bit later. But just for simplicity, we assume sigma is known, and X is observed on this grid, and skeleton W n, that's the notation, is formed by reordering independently sampled normal increments according to the order of the X increments. Now the recovery result is stated here. We have a convergence in probability. So there is this Brownian bridge approximation converges to the true Brownian bridge, and that happens in supremum norm, and we'll study the convergence rate of that. And if you want to recover also the signal, well, we can just subtract from X, we can subtract this scaled bridge thin, and we'll get Y up to a random trend, right? So just because you have here discretization, that's what is available to us. I need to use Skor-Hod J1 topology, but if I'm, if I restated results somehow, like we only care about the grid points, then convergence will happen in supremum norm and with the rates we discussed below. Anyways, so this is recovery is possible. That's the bottom line. And when we study the rates, we'll just look at convergence of Brownian bridges in supremum norm. So very important that that this reordered thing, Wn, is still a skeleton of a Brownian bridge, right? But when you look at them jointly, W and Wn, at the skeletons jointly, this will not be bivariate random walk anymore, because you reorder one using the ordering of the increments of the other one. But what is still true is that the increments are still exchangeable, and that's the main tool somehow in the analysis of this convergence. Okay. So to get the rates, somehow the understanding of the rate of convergence, I need to say a few words about Lévy measure. So the Lévy measure describes the jumps of the Lévy process. So the assumptions are that it is finite away from the origin, and it should integrate x squared at the origin. Well, the common interpretation, there are many of them, but one is that if you restrict this measure to some set bounded away from the origin, like you see here, you exclude minus xx, then it should be finite, and the corresponding Lévy process will be just the compound Poisson. Its rate of jumps will be the total mass here, and the distribution of jumps will be the scaled Lévy measure, right? That will be the measure of the distribution of jumps. Right, so what we care about is the behavior of the process Y at small scales, right? It's only the small scale, small time behavior of Lévy process which matters. And that is characterized by the behavior of the Lévy measure at 0. So what we need to somehow understand or quantify is how this Lévy measure behaves at 0, and one standard assumption is to assume regular variation at 0. So I say it's just of power form times some slowly varying function. So alpha is necessarily in between 0 and 2. Slowly varying function, for those who haven't seen these things, is just something convergent to a positive constant or a logarithm or power of logarithm or double logarithm, something which behaves nicely and slower than a power. Essentially, right. And what else I should say? I should say that if alpha is 0, then essentially the process is almost like a compound Poisson. It's gamma, so gamma process corresponds to alpha being 0, for example, right? As you increase alpha, the small time, so the small jump activity becomes larger and larger. And at alpha being 1, we can get, say, Koshi process. And this is the boundary where we get from bounded variation on compacts to paths of unbounded variation in compacts. So alpha being 1 separates these two classes somehow. And alpha being 2, so you can actually have alpha 2, and that will be extremely close to Brownian motion on small scale. So it should be very hard to separate the two processes because they will look very much alike, and one can make it precise on small time scale. So the rate is essentially given here. It's n to the power 2 minus alpha over 4. So you see, if alpha is 0, as I said, it's something very simple now. Then we have square root convergence. When alpha goes to 2, the rate deteriorates to well, arbitrarily bad rate actually. And this is what one expects intuitively. The precise statement is here. So for every positive epsilon, if you look at this supremum norm, right, you take the difference between the two bridges, and you look at the supremum of the absolute value multiplied by this rate minus epsilon, then there is convergence in probability to 0. For every negative epsilon, this convergence fails. That's why I know I can say this is the rate in logarithmic sense. So at least we know exactly the power of the rate. But of course, there might be some slowly varying or some other factors, second order terms here. Also, we say when alpha is 2, then of course this result doesn't tell us yet that there is convergence, but in fact, what we say alpha is 2, we can take epsilon 0, and then we say that there is simply convergence to 0 in probability. So indeed, approximation works. recovery works in all cases, even when alpha is 2, but for alpha being 2, we cannot say anything about the rate. And well, this result is actually much more general than I have presented. Why? Because now you can employ Girsanov's theorem to your advantage. So what we can do, we only need to assume that W is a Brownian motion under some dominated measure, underlying dominated measure, right? So for example, you can easily take, say some diffusion, some Bessel process. There is example here below, whatever. So I don't want to go into details, but one can actually do things in a more general setting just by using this change of measure trick. Right, but throughout this talk, I will concentrate on Lévy process setting and will not go any further. Also, the process Y can be a bit more general. You can introduce a bit of dependence between W and Y, but not much, because you will see exchangeability of increments is essential in the proof. And finally, one can deal with multivariate cases, multidimensional cases, right? Essentially, you apply the same trick in each dimension and you're done. So there is not much to say even, you know, adaptation to multivariate setting is pretty much straightforward. Yes. So this is how it looks numerically. We tried an alpha stable process Y with different stability indices. So as you know, convergence rate depends very much on this alpha. So from 0 to 2, where convergence should be fast, to all the way 1.99. And let me see, this is a log-log plot, of course. So we know that the theoretical rate, these lines should be with this slope. As n increases, the error should decay in the logarithmic sense as -2 minus alpha over 4. And what we have done, we have simulated numerically those errors. The errors were taken over some dense grid. I think it was 10 to the power 7 used to calculate the supremum. So we just replace supremum by the maximum in the simulations. And I don't know anymore how many samples they were taken. But anyways, these are the simulations. And the lines, they depict the theoretical result. And we just anchor these lines at midpoint at 10 to the power 5. So all the lines, we know their theoretical slope. And we simply anchor exactly at the midpoint and see how well it projects back and forth. Yeah, and you see that the theoretical result actually, yeah, suggests a very good approximation of what happens in practice. By the way, what time should I finish? I never asked. How much time do I have for this talk?
Sorry, you have half an hour.
Half an hour in total or to go?
From now.
Okay, okay. I think I'll take less, but just to be sure. Right. Yes, so the above result is about logarithmic rate, essentially, right? So one can ask, why don't you try to be a bit more precise about the rate and about the limit result? So this is what I'm trying to do next. And this we could only handle for very simple processes Y. And the problem becomes really complicated when you have infinitely many jumps. So what we assumed is that Y is a piecewise constant or piecewise linear, the same thing, because you just look at the ordering of increments. Well, the slope should be the same, of course. Let's say Y is piecewise constant process independent of W, and jumps are denoted by J and times are denoted by T, right? In fact, we don't need to assume that it is a Lévy process. It can be any piecewise constant process as long as it is independent of W. That's the only assumption here. And then we apply our trick. We construct this Wn, the skeleton of this Brownian bridge. And now we look at the difference of those bridges. Right now, I actually, we substitute here discretized version, right? We only look over the grid points at this difference. That's important for this case. And the rate becomes square root n over log n, right? So why do I need to look at discretized version here? Simply because discretization itself has the same order of magnitude. That's the standard result. You can, well, maybe I'll say a few words about that later. And there is convergence in probability, and what you see on the right-hand side in the limit, that's kind of structure for the exchangeable process. You see those jumps essentially. Sorry, at the time of jumps, I have unit jumps here in the limit process, and the sign. So the original jumps of y, they matter only, they appear up to the sign only, right? Only their sign matters, nothing else, not the size, not the magnitude. So you see, it's pretty clear, right, what happens. So we, of course, need to get back to 0, and you have this zigzag thing with jumps of unit size, depending, of course, on the sign of j. I think here they're all somehow negative, but so j is probably where all positive then. Right, and that's the simulation. You see limit in black, in solid, and pre-limit in these gray shades of gray. Here we need Scarhard J1 topology, of course. Right, there is also another result. So far we have assumed that sigma is positive and it's known. So what happens if sigma is actually 0, if there is no Brownian part? What I'm saying, you have a Lévy process, you don't know a priori if there is Brownian part or not, but you can still just reorder the increments of this Brownian trajectory, of the independently sampled Brownian trajectory. So you can easily form this Wn. Doesn't matter if you have Brownian component or not, but it turns out, even though you reorder the increments accordingly, in the limit, the two things will be independent. So in the limit, we have distributional convergence to x jointly with b, where b is just a standard Brownian motion independent of x. We could only prove this result for alpha being smaller than 2. I believe it holds in general. It just needs much more precise estimates for Lévy process. Right. So this is in particular gives you, provides a way how to maybe construct a test for presence of a Brownian part. But let me now discuss possible applications. So once again, we first observe something and then try to come up with applications. But I hope they are persuasive enough anyway. The first thing is that often we interpret these parts of the ET decomposition as signal and noise. So Y, you can think of Y in many settings as a signal process and W as a noise. So what we do essentially is we just do signal noise separation. And well, there are various papers in physics and signal processing where they look at these kind of models. And then you can also, our results immediately give some convergence rates on some derived quantities. For example, you want to estimate, I'm saying estimate, but it's not that we estimate some deterministic, some parameter, we estimate a random quantity here. You can, for example, estimate signal fluctuation around its trend. So maximal signal fluctuation around its trend. So this is what I mean. And you can try to estimate this quantity when you're given just a sample path. Discretely observed sample path of X, where you have also noise W. As I mentioned before, one can do, for example, one can imagine testing for presence of Brownian component. There are various statistical procedures which may benefit from pre-separation of the Brownian part. So normally, people apply some kind of thresholding techniques, and it has been shown numerically that these thresholds are very sensitive. So the choice of threshold can badly influence the quality of the estimate. Right. So what we suggest, one can try apply this procedure to separate first the noise and then maybe to apply the basic statistic on that signal Y there. So I should mention that simpler problems, of course, will suffer from these suboptimal rates because we consider a pretty complicated problem, right? We try to separate paths. But nevertheless, this approach allows to avoid this difficult problem of threshold selection. So that's the advantage. And finally, let me mention a coupling between a Lévy process and a Brownian motion. So what I have presented can be used to couple Lévy process with a Brownian motion, which is needed in all kinds of applications, starting from multi-level Monte Carlo methods, and going to model risk and estimating Wasserstein distance and things like that. So this is actually where we started. And now we have a new paper upcoming where that's the main focus, how to couple a Lévy process with a Brownian motion. And these applications, this was our main focus somehow, multi-level Monte Carlo and model risk. So the main message is that you can actually still employ this reordering idea, but one should not push too far. So it's not a good idea to take too small intervals. One will be, I mean, there is a trade-off. You should split and reorder them on a rather fine scale, but not too fine. So there is a very nice result on the optimal split of on the optimal choice of this discretization grid when you want to couple a Lévy process with a Brownian motion. All right. So I have come to proofs. Since I read on the website of this seminar series that people should not only share their results, but also give an idea of methods and how they can be applied. So I decided to say a few words about the proof, and I'll give some ideas how to of the proof of the very basic result here, and that's it. So I will look at the this maximal difference between the bridges when multiplied by the suggested rate, and show that it does converge to zero in probability. So the first fact is that, which I have mentioned before already, that discretization error of the Brownian motion is it's just log n over n square root, right? So it behaves slightly slower, decays slightly slower than square root. And that's easy to see. You just scale it with square root. You have a maxima of IID, maxima of Brownian motions, and just extreme value theory gives you this rate, more or less. So this rate is, of course, much faster than the rate here for any alpha. Even when alpha is 0, we have n to the power 1 over 2 minus epsilon. So you have still a faster rate than this one. So we can ignore discretization problems. So we can just look at the maximum over the grid epochs, essentially. Right, so I will forget about the suprema over time 0, 1, but I will look only over the grid now. So over the grid, we have these increments. So these are the increments. I rewrite this Wn as the permuted increment of W prime. Remember, W prime initially is independent of W. Now pi I makes sure that increments of this guy coincide with increments of X. And this second term comes simply from, this is the compensating part because we look at Brownian bridges. Right. Now I take this square root, which sits in here. I multiply all the terms by square root. So I have standard normal quantities, right? All of these things are standard normal now by scaling. And initially, once again, Zi's and Z prime i's, they are independent standard normal IID sequences, and pi I is this random permutation which makes sure that the ordering of Z prime pi I coincides with the ordering of this delta X of the increments of X. right? The ordering of x does not change if we scale it. So I can just scale by square root also that part. And you see the ordering of z prime pi I is the same as the ordering of zi plus these scaled increments of y. Right, so this is where we start. We want to show that this quantity goes to 0 in probability. And what do I do next? I will try to separate it into subproblems. So I will introduce this another permutation nu I, such that z nu I has the same order as z prime pi I. So all of these things, z prime pi I, z nu I, and this zi plus the increments of y process, they have the same ordering. That's the trick, right? And then I just add this thing here and subtract here. So it's just what we had before, but now we have two parts. Why do I like these two parts so much? Well, firstly, now the ordering here coincides, right? The ordering of z permuted and z prime, they're permuted according to the same thing. And here I have the same sequence, right? Not so there is no prime on the right-hand side, in the right term. So these two things will be denoted by tilde and hat. And the very important point here is that these things are still they are exchangeable. The sequences, the increments of the increments xi tilde and xi hat, they are exchangeable. So why are they exchangeable? We just need to apply permutation and see that the distribution doesn't change. Well, if you apply any permutation to this thing, if you permute these things, that will essentially correspond to permuting all the original quantities and then just redefining the problem. But the original quantities, they are IID, so when you permute, they will have just the same law. So it's very easy to see that exchangeability is there, and the same goes is true for the right. So for the second part, permute, that corresponds to permuting these original quantities, and that's just has the same law. So as soon as we have exchangeability, there is general theory. So those exchangeable increment processes, they converge normally to an exchangeable process. I just wrote here Kallenberg, so you just open this foundations book or invariance and symmetries book, and there are all kind of results which specify, which gives you conditions, if and only if conditions of convergence, right? So in general, this exchangeable process, so which has exchangeable increments on all levels, it has this nice form where I don't need it actually, but just for reference, BT is a Brownian bridge. All components are independent. U's are uniforms. So you kind of see that part which has appeared in one of those propositions when we talked about precise limit results, right? So it's a bit similar to a Lévy process to some extent, but it's not. What is important that these increments we have just defined, they sum up to 0, right? So you see, if you sum up those increments here, you will have 0 because of this compensating term, and here these are just permuted. It's the same sequence which is permuted differently, but when you sum it up, of course, you will get the same value, so it cancels out into 0. Right, we have these two things which are 0. And then we also aim for the 0 process limit, which is of course exchangeable process. And then, so Kallenberg's book gives us a very simple condition. All we need to show is that if you sum the squares, then those must converge to probabilities to 0, right? So the only things we need to show now is that this series, these sums, they converge to 0. So nothing about processes anymore. We can forget about particular orderings. All we need to know, we need to just take care of orderings inside each increment somehow, but not the ordering of those increments themselves. So let me be a bit more precise here. So the first term which you see here, in fact, is very easy now. Why? Because z nu I and z prime pi I, they are ordered according to the same thing. So they have just the same ordering. And I need to sum them up. So I can simply take order statistics. I take standard normal, two independent sequences, z and z prime of standard normals. I look at the order statistics. So z brackets I and z prime brackets I. And this is, I take squares, I sum them up. Of course, this rate is still sitting there. Well, it's a square now of that rate. And this must be going to zero in probability. Now, this part does not depend on I. So one can easily rewrite and show that this is negligible, essentially. And what is left to show that this goes to zero. But this is closely related, of course, to empirical quantile functions. And there are all kinds of results. And in fact, there is convergence to zero in probability as soon as this factor in front has this order. So you must ensure it goes faster to zero than 1 over log n. But here we have a power sitting, so there is no problem. It goes to zero in probability. So just some basic theory on empirical quantile functions for standard normals. Right. What about second problem? This is much more interesting. Well, maybe I should mention that if there is no Brownian, no jump part, if there is no y, the proof is complete, right? That's it. There is no second part. What about second part? In general, we have y. So we need to show that sum of squares here goes to zero with this rate. And recall that z, now we have just the same sequence, z, there is no prime anymore. And permuted z nu I has the ordering of zi plus this thing. So the idea is that the Brownian part, we all know it dominates the jump part on small scales. So you expect that this guy is much larger than this guy. So you, what happens, you take one sequence and you reorder it according to the noisy sequence. So I just interpret this thing as a small noisy contribution, which somehow spoils my ordering. So the ordering does not coincide exactly, but it's almost there. But we need to quantify that. So what we were able to do, we proved this reordering bound. So now I can, once again, there is no probability here. It's a very nice combinatorial exercise. Well, I wrote here, it's an excellent math competition problem. It took us a few days to actually state and prove it. But I guess for those smarter guys, they can do it in half an hour. So it's a really beautiful problem. So if you have some spare time, I'm very much advising to try it. So what is it here? We have an ordered sequence of z's, z1 up to zn. These are just ordered real numbers. Then we take some arbitrary y's, and we just reorder. So we find this permutation such that, as here, right, the ordering of z nu I coincides with the ordering of this z plus y sequence. So nu I is simply the rank of z plus y I. And we need to look at the sum of squares of square differences. And this bound says simply that there is what you can take is the sum of those noise variables squared, minimum m squared, where m is just the span, is the maximal distance between z. So it's just zn, the largest minus the smallest. Okay. That's the bound one can show. It's not a long proof, but it's this combinatorial thing which takes time. But when you see the right perspective, it becomes kind of rather simple. Now I can apply this bound directly. So you see what I need to take care of. I just need to take care. I need to take care of the convergence of these delta y things. So here it is. Well, we need to be a bit careful, right? First of all, what is the we need the difference between the largest z and the smallest z squared. But it's just the maximum of normals, right? We know it behaves essentially as log n, right? It's bounded in probability by log n. So I can replace in my bound that m squared by log n. So let me go back. So this is where log n will stand. And now I have to take square of this term, which gives me n times delta divided by some constant, which can be ignored. So the constants are ignored, and you have this expression here, right? So we need to show that the sum of these things goes to 0 in probability with a certain rate. Well, for that, it's sufficient to show L1 convergence. So we just take expectation. And now all these things, of course, deltas, they have the same distribution. So you just look at one of them, at the first one. You have n such terms, so n goes in front, and I also take n from this bracket. So you have y squared 1 over n, minimum log n over n, expectation. It goes to 0. And so we have reduced the problem to essentially behavior of these truncated moments at 0. And one can use some standard arguments, but it's rather tedious. So it still requires quite some work, but it can be done using standard arguments. So I will not provide any details of that. And that's it. That concludes the proof, if you believe this estimate. And this is how we found the correct alpha. So this expectation, of course, can be bounded in terms of the Lévy measure, and then you see what alpha should be there. So what kind of power should be here. All right. Now, this is my one slide about the alternative method. And an alternative method is based on threshold filter. So what I want to do is the following. Somehow we have a Brownian part and a jump part, which we want to separate. So what is a jump part? It should jump, right? So what you do is you say everything, all the increments which are larger than some threshold, they correspond to the jump part. And all the increments which are smaller than some threshold, they correspond to the Brownian part, to the continuous part, right? And it's immediately clear that one should be very careful with the threshold AN. One can see more or less that roughly it should be of order square root n, but one needs to be much more precise. So what we could show is that the right choice of threshold AN here, which you use to separate your increments into Brownian, non-Brownian part, and then you just accumulate those increments separately. That's how you construct the approximations of W and of Y. So it should be, again, n to the power minus 1/2. That's kind of intuitive. And then there is Ln thin, which should behave slower than any power, but faster than this term here in asymptotic sense, as n goes to infinity. So it should behave faster than square root log n with some constants, precise constants, but slower than any power of n. In this case, we can show convergence in probability here. So we can show this recovery. Now, the advantage of this method that somehow you don't need to know about sigma. Sigma is in there. So what you recover is a Brownian bridge scaled by the appropriate sigma, by that sigma. And we can also show that the rates are just the same as in our reordering method. So with this very particular choice of threshold, the rates are the same. And we could also show that the rates become worse if you are not careful enough with the threshold. Another important thing is that this term here is extremely important. So one cannot forget about this term, and maybe that's why we were surprised. There were no results in the literature about these kind of things. And one reason might be that in the case of unbounded variation of paths, so when the jump part has unbounded variation, if you forget about this term, this guy will simply explode in many cases. There are things like a stable process with only positive jumps, and you take that guy to see that such an estimate without compensating term will just explode as n goes to infinity. So this is very important to subtract the compensating part, and then we recover the bridge. If, however, y has finite variation in compacts, so it's something like a compound Poisson, well, it's a simpler process to separate, then you don't need to compensate. One can avoid compensating, and then what you recover, in fact, is the scale Brownian motion plus the linear drift. So this allows one to separate this linear drift from the signal. So now we cannot separate drift from the Brownian motion, as I explained before, but we can separate drift from the jump part. So that's the message here. And if you don't compensate and you want to separate this drift, then the rate deteriorates again. The rate becomes slower. The same rate 2 minus alpha over 4 when you have compensation in general, and the rate is similarly, I write similarly here because we only proved an upper bound, but not a lower bound, 1 minus alpha over 2. So it's a slower rate, and it actually only works when alpha is below 1, yeah, when you have finite variation. In practice, it's a bit problematic because you still have this tuning parameter, and I have mentioned before, this separation can be actually very sensitive to the choice of the tuning parameter. We have made small numerical comparison. Once again, alpha is 1.2. We take an is just log n over square root n. Such a thing would always work here, right? It's decays, log n decays slower than any power, but faster than square root log n. So that's fine. And then what we got is this thing where you see actually method 1 on reordered with reordered increments and no threshold works a bit better. And in fact, you can see a constant factor of improvement here.
2 minutes left.
But what?
Sorry, 2 minutes left.
Once again, this thing with threshold is quite sensitive. So if you play maybe with this threshold, you might be much worse or maybe even better than the reordering method. Right, so just a summary, some conclusions. So method 1, surprising, first of all, no tuning parameter. The convergence rate in the logarithmic sense is n to the power 2 minus alpha over 4. Which deteriorates as y becomes closer and closer to the Brownian motion on small scale, and which is almost square root when you have something simple like compound Poisson process. We have identified underlying reasons, and we talked about possible extensions. In some particular case, when you have piecewise constant y, we were able actually to get the exact rate and the limit process. And also when sigma is 0, when there is no Brownian part, that we saw that you get independent Brownian motion if you do this reordering in the limit. Method 2 with thresholding, so compensation with the final value is crucial, otherwise it might the estimate might explode. It has the same logarithmic rate for a carefully chosen threshold, and you can also do it without compensation in the case of bounded variation of jump part. But then you get a slower rate, and as an advantage, you can separate drift, a linear drift, from the y process. That's all I wanted to say. And if you want to have a look at the paper, it's gonna appear in Bernoulli, and there is a link to the arXiv version. Thank you very much for your attention.
Okay, thank you very much. Any questions, comments?
I ask a question.
Yeah, please.
Zhenya, the alternative method is very natural. That's what perhaps I would start doing. Maybe I missed it. How did you come up with the first one, with the ordering one?
That's a good point. As I mentioned, we didn't start with this problem at all initially. So that was not on our agenda. We were trying to couple a Lévy process with a Brownian motion, and we didn't know enough of the literature. So we didn't know about various methods. We knew some, but not everything. And then we just tried something. And this something was very surprising. And then we tried when we saw that those Brownian, so that the Brownian bridge is determined by the ordering of increments, on infinitesimal scale. We try to understand and we try to apply that thing. But you're right, as soon as we came to the problem, then of course this method is much more straightforward.
Yeah, so
one still needs to be very careful because of this compensating part. And it's not easy to get the rates, but it's way more straightforward than the other method. Yeah.
So it was serendipity approach, the first case.
Yes, kind of.
Any other questions, comments?
Thank you. Very nice talk. I have a small question maybe about extension. So you started with this Lévy decomposition where you have the standard Brownian motion and you have this jump part. So if I just forget about composition and look at this problem that, for example, the first part is not standard Brownian motion, but fractional Brownian motion plus jump part. So can you use the same approach? Because you can have some type of dependence between increments and
Right. So I mentioned before that these results are much more general in the sense that we can play with change of measure. I don't think fractional Brownian motion fits here, but definitely the results are much more general. So I gave this example here that okay, you can go to some diffusions. That's one possible extension, right? So all you need to do is that there is a dominating measure under which your W is a Brownian motion. And then, of course, if you have convergence under that dominating measure to zero in probability, you also have convergence under this measure P.
Mm-hmm.
Right, that's one extension. Another one is multivariate version, which is kind of straightforward. And then you can also introduce some dependence because all you need is, we have this assumption on exchangeable increments, but that's still kind of a strict assumption, right? Mm-hmm. But you know, the bottom line is that you need some machinery, and martingale methods here, they simply do not work because you reorder the increments, right? So somehow this exchangeable structures is the natural thing to look at. Mm-hmm. Right, so I can't really answer your question, but just to tell that it's much more general than I have presented.
Mm-hmm. Okay, thank you.
So for example, all the simulations I showed, they were done for Bessel III process, not for Brownian motion. Mm-hmm.
In multivariate case, you order, do you assume any dependence between components? So it works in general case as well?
You don't care about dependence between components because you can recover with probability 1 each component separately.
Okay, so basically you do it separately.
Yeah, you just do it separately.
Okay.
You can do it together if you know you have a smaller rank of the covariance matrix, then you can of course save some time, but yeah, just apply separately in general.
Okay. No more questions? All right. If there are no more questions in the comments, let's thank the speaker for the interesting talk. Thank you very much.
Thank you. Thank you very much.
Thank you.
Okay. Bye-bye. Take care.
Bye.
Thank you very much for the nice talk. Okay.